Hi, this is part of FRM Part 1, Book 2, which is titled Quantitative Analysis. And this specific video is on Chapter 2, which is titled Random Variables. So I will try and keep this video short, and if I cannot cover all the various learning objectives, I will try and make this a two-part video. So one of the first learning objectives is to explain what's probability mass function and what's a cumulative distribution function. Now, before discussing what do we mean by probability mass function, one of the first things you need to understand is that there are two types of variables. Now, there's a variable which is called discrete, and also there are variables which are called continuous variables. Now, when we talk about discrete variables can only take specific values. In other words, finite number of values. For example, if you toss a coin, you will either get heads or tails. Or for example, if you roll a dice, you could get 1, 2, up to 6. So you can see these events can only give you specific values, or in other words, finite number of values. So with these kind of variables are called discrete random variables. Now, continuous random variables, for example, if someone asks, what do you think a particular stock will return tomorrow? In other words, how much will the return be? Would it be 5%? Could it be 5.2%? Could it be 5.8%? Or could it be 1%, etc.? So you can see these variables are continuous. In other words, you can keep going. For example, you can say, can it be 1.1%? Or can it be 1.1112%? And you can keep on going. So for example, if we talk about a stock return, it can take infinite number of values, and that's the reason we normally we wouldn't say a specific amount. We will say, for example, what's the probability of the stock returns being between 5% and 10%. We always talk within a range. We will not specify a specific number because the variables are continuous. So remember, there are two types of variables. One's called discrete variables and the other one's called continuous variables. Now, when we talk about probability mass function, we are basically referring to discrete random variables. So here I'm showing you an example. So this particular variable x can take these values. It can either take 0, 1, 2, 3 or 4. So you can see these are very specific values. So this variable can take these specific values, and the probability of getting each of these values is as follows. So for example, there's a high chance that this variable can get 4, because you can see there's a probability of 35% of this random variable getting 4, and there's a very low probability of this random variable getting 3, because there's only 5% chance. And of course, the sum total probabilities will add up to 100. The sum of all the possible events should add up to 100. Now, if I show this in a particular diagram, so let's say, for example, I have x, this particular random variable can either take 0, 1, 2, 3 or 4. And let's assume that these are the various probabilities. So for it to take 10%, let's assume that that's 10%. That's 30%, or 20%, 3%, or there's a very high chance of getting 4, 35%. So this is what we call it as a probability mass function. In other words, a probability mass function will show you, or it can be used to calculate the probability of a discrete random variable. So remember, when we talk about probability mass function, we are referring to discrete random variables. So when we refer probability mass function, we are referring to discrete random variables. So Another concept that's closely related to the probability mass function is called probability density function. Now remember, when we spoke about random variables, we said there are discrete random variables and continuous random variables. Now, for example, if we are talking about stock returns, what's the probability of a particular stock returning? Let's say tomorrow we are asking a question. What's the probability of a particular stock returning between 5% and 10%? What's the probability of a stock returning between 5 to 10%? Now, of course, we said that when we talk about stock returns, the returns are continuous random variables because it can take infinite number of values. So for example, it can be, for example, the maximum negative value a stock return can take in percentage terms is minus 100%. Remember, because minus 100% means the stock has lost all its value. And let's say, so this is 1%. So you can see, let's say it has a particular probability of getting 1%. There's a particular probability of getting 5%, 5.1, 10%, 6%. So what I'm trying to show you is that for a continuous random variable, you will not have any gaps in between, because remember, I'm just showing you very high level. You can have 5%, 5.01, 5.001, 5.008, etc. So what I'm trying to say is the probabilities will be, all the bars will be close to each other. You can draw a curve like that. I'm just kind of drawing a curve. It doesn't have to be a normal distribution. But what I'm trying to say is, for a continuous random variable, that the distribution will look something like this. So this is called a probability density function. So that's a probability density function. So remember, the probability mass function and probability density function basically shows us the probability of a particular event occurring. Now, probability mass function is to do with discrete random variables, and probability density function is to do with continuous random variables. So that's what you need to understand. Now, another term that's closely related to these distributions or these functions are called cumulative distribution function. Cumulative distribution function. Now, cumulative distribution function is quite simple. It's closely related to the probability mass function or the probability density function. What a cumulative distribution function does is that, as you can see from the word itself, it's cumulative. It gives you the cumulative probability of a particular event occurring or any other event occurring less than that particular value. So for example, here I'm showing you. Now, the probability of x taking 0 or any other value less than 0 is 10%. So basically it's the same as this. Now, the probability of x taking 1 or anything less than 1, that means we know that this is a discrete random variable, so if x doesn't take 1, it will take 0. So the probability of getting 1 or anything less than 1, you simply add these two probabilities, which is 10% and 30%. That's what we are saying here. That's 40%. So here the probability of x getting 2 or anything less than 2. So that means the probability of getting 2 or 1 or 0. So we simply add all these three probabilities. So 20%, 30% and 10%. So that gives us 60%. So that's what you can see here. It's 60%. So a cumulative distribution function gives you the cumulative probability of getting a particular value or any other value less than that particular value. So we say that a cumulative distribution function would look something like this. For example, it will start from a lower probability value. So this is, let's say this is x. That means this is the different values you can take. That's the probability. It will keep increasing up to until it becomes 1. Remember, because cumulative distribution function, you can see the maximum is 100%. So the cumulative distribution function would look something like this, whether it's for a discrete random variable or if it's for a continuous random variable. So we also say that a cumulative distribution function is monotonic. That means it keeps increasing and it's continuous. So remember, a cumulative distribution function is monotonic and it's an increasing function. As x increases, the cumulative distribution function will keep increasing. Now we are going to look at another important concept called expectations. So remember, this particular topic, expectations, is quite a key topic since it can come across in various sections in book 2 in quantitative analysis. Now, the term expectations is closely related to the term mean, but they are not the same. So what do we mean by that? Now, assume, for example, let's assume that you have a particular stock and you have data for the last 250 days. You have data for the last 0 to 250 days of that particular stock's return. Now, if we want to know the expected return of, let's say, stock X for tomorrow. So what's the expected return of stock X for tomorrow? What we are saying is that, of course, we have the returns for the last 250 working days, and we want to calculate the expected return of stock X for tomorrow. We are going to know what we'll normally do is we will take the average of all the 250 returns. So let's assume we have various returns and we are getting the average, and let's assume that that's 3%. So you can see, since we took the average, the calculation is same as calculating the mean, but there's a slight difference because mean always looks, it's a backward looking term, whereas when we talk about expectations, we are talking about the future. So remember, that's a slight difference when we compare it to the mean, but the calculation itself is similar to calculating the mean. Now, if we have a particular variable, so here I'm giving you the possible values that you can get if you roll a dice. So you can get 1, 2, or 3, or 4, or 5, or 6. And the probabilities of getting each of these numbers is simply 1 over 6, because you have 6 different values, and the probability of getting one of these values is simply 1 over 6. Now, if there was a question that what's the expected value? If you roll a dice, what's your expected value? What you do is you simply sum all your values. So you can either get 1, 2, 3, 4, or 5, or 6. You sum them by multiplying those by the relevant probabilities. So that's what I'm showing you here. So that's your X. You can either get 1 or 2, 3, or 4, or 5, or 6. The probability of getting each one of them is the same, 1 over 6. 1 over 6. And you simply multiply them. So here I equals 1 to 6. Remember, you can get, if you roll a dice, you will get one of these numbers, 1 to 6. So the expected value of X is, you multiply each of the probabilities by its value, which means you will get 3.5. If you add all this, you will get 3.5. Now, of course, you might be thinking, if I roll a dice, I'm not going to get 3.5. But what we are trying to say is, remember, if you roll a dice, the average, the middle two numbers are 3 and 4. So that's what we are saying, you will get something somewhere in between. So the average is somewhere here. So that's what the expected value is 3.5. So if you are given a random variable such as this, and you are given the probabilities of that random variable getting each values, and if you are asked to calculate the expectation, you simply multiply each value by its probability, and that will be your expected value. Now, one thing to remember is that expectation is a linear operator. Expectation is a linear operator. So what do we mean by that? Now, that means the expected value of a constant, for example, expected value of $10 is $10. Then also the expected value of the expected value of X, for example, something like this. What's the expectation of the expectation of X is simply the expectation of X. So remember, the expectation parameter is a linear operator. So what this simply means is, let me show you an example to kind of grasp this concept quite clearly. Let's assume that you have two bonds. You have two bonds, bond A and bond B, both has a notional of $100, and the expected return of bond A, let's assume it's 2%, and the expected return of bond B is 5%. Now, if you are asked, let's assume that you have a portfolio with some cash, $1,000, plus you have 5 bond A's and you have 2 bond B's. So the question is, what's your expected return of this particular portfolio? So what we could do is, remember we said the expectation operator is a linear operator. So what we could do is we can write this as expectation of $1,000 plus 5 times the expectation of bond A plus 2 times expectation of bond B. We know that this is $1,000. This we can simply multiply 5 times expectation of A is 2% and 2 times expectation of B is 5%. And that will give us the answer. So remember, the expectation is a linear operator. Now another thing to remember is that the expectation operator does not fit non-linear functions. So remember, the expectation operator does not fit non-linear functions. Now what do we mean by that is that the expectation of 1 over x is not the same as 1 over the expectation of x. So these two are not the same. So remember, the expectation operator does not fit nonlinear functions. That's quite important to remember. The same way, the expectation of x squared is not the same as expectation of x whole thing squared. So these are not the same. So remember, an expectation property fits linear functions, but it does not fit nonlinear functions. And in a FRM exam, you could be tested on this quite a lot. So it's better to practice some questions and get very familiar with the concept. In this section, we are going to have a look at some of the population moments. Now, what do we mean by population moments? So moments are statistical parameters that helps you to describe a particular distribution. So the first moment is simply the mean. So remember, the mean of a particular distribution or particular range of data tells us the average of that distribution. So for example, if you have stock returns for the last 250 days, for each day if you have stock returns, the mean of those returns will tell you what's the average return that you could expect over a particular day. So that's the first moment. So it tells us something about the data. Now the second moment is called variance. Now the second moment is called the variance. Now the second moment is called variance. The variance basically tells us what's the noise in a particular random variable. So if you have, for example, if you have a variable such as this, so let's assume that this is a particular distribution, and you have another distribution such as this, you can see that the one in red has a larger variance. So that means the dispersion of this random variable is much more compared to the green one. So variance tells us how spread the data is. Now of course you can calculate variance using this formula, the expectation of x minus mean whole thing squared. So the variance tells us simply how spread your data is from the mean. So it's the square of your spread. Now of course the square root of variance is called the standard deviation. The square root of variance is called the standard deviation, which is normally used when we talk about volatility. Standard deviation is an important concept in risk management, which is used sometimes to refer the riskiness of a particular asset or to measure the volatility of a particular asset. Now the third moment is called the skew. Now skew measures the asymmetry of a distribution. So what do we mean by this? So for example, if we have a distribution similar to a normal distribution, we know that it will look something like that. So that's let's just assume that's a normal distribution. So you can see that a normal distribution is symmetrical. It's symmetrical. Now there are other distributions that can have a long right tail or a left tail. So for example, you can have a distribution something like this. So you can see this distribution, the one in red, it has a long left tail. So something like this, we call this red distribution, we can call it, this distribution is negative, it has a negative skew. In other words, it has high probability of having large negative values. Remember, normally as you go to the right, your values increase. In other words, your values increases, and as you go to the left, your values decrease. So compared to the green distribution, if you look at the red distribution, it has a long left tail. So we call it a negative skew distribution. Now normally asset returns are negatively skewed. In other words, there's a high probability that they can have large losses than large profits or large positive returns. So a skew can be measured simply using this formula, the expectation of x minus mean divided by the standard deviation to the power of 3. Also remember, a skew is a unit-free parameter. In other words, you can use the skew of various distributions to compare them and to comment on them. So which is quite useful. Remember, a skew is a unit-free parameter. Now the fourth moment is called kurtosis. Now kurtosis is used to measure fat tails, or we can call it heavy tails. So for example, if you have a normal distribution. A normal distribution has a kurtosis of 3. Now, there are other distributions that can have a kurtosis more than 3. For example, let's assume that this is another distribution. So you can see the distribution in red, it seems to have large negative values, and the probability of getting these values is quite high. Because remember, the probability is defined by the area. The probability of getting negative values are quite high. Compared to the normal distribution, the area is quite small. If you look at the area in the to get the same value in the normal distribution, it's very small. The area is small compared to the area under the curve for the red curve. So the red curve has a kurtosis greater than 3. You can say this one, this distribution has a kurtosis greater than 3, and we call this excess kurtosis. Now you can use this formula to calculate your kurtosis. Simply the expectation of x minus divided by the standard deviation to the power of 4. You can already see that kurtosis will always have a positive value because it uses the power of 4. So if you have a kurtosis less than 3, then that kurtosis is less than the kurtosis of a normal distribution. If you have a kurtosis which is more than 3, then we normally call that as an excess kurtosis, and that means there are large probabilities of getting extreme values. It can be either positive or negative. So these are moments. So remember, moments are used to describe your distribution. How risky is your distribution? Because you could have two distributions or two different portfolios which can have the same mean. It can have the same mean and it can have the same standard deviation. Now in that case, you need to look at that those two distributions, skew and kurtosis, before deciding which one is the best portfolio to invest. So for if both have the same mean and same standard deviation, you can look at the skew and the kurtosis of those two portfolios to decide which portfolio might be beneficial to invest. So these are some of the reasons that moments can be very useful. Let's look at what is a quantile function. Let's look at what's a quantile function. Now, the word quantile refers to dividing something into groups. So, for example, let's assume that we have 30 students in a classroom and we are measuring their heights. So some of their heights will be less than the others, and there will be some who are much taller, and there will be much who are much taller, etc. Now, if we want to know kind of the middle range, in other words, where 50% of the students are more than a particular height and 50% of the students are less than a particular height, then we need to find out kind of a middle range to say, okay, that this 50% of the students are more than, for example, let's say 4 feet, and 50% of the students are less than 4 feet. So that particular, so we know that this is referred to as median. Remember, median is the middle value. So remember, median is the middle value. So we can say something like this. So we can say the probability of height height, which is a variable, being less than or equal to 4 feet equals 50%. So we can say something like this: the probability of height being less than or equal to 4 feet equals 50%. So in this case, now this is a quantile. This is a quantile. So when we talk about quantiles, what we are trying to say is that we can divide data into various groups. So I'm just kind of loosely trying to define this to you. So I'm just trying to loosely define this for you. So when we talk about quantiles, what we are saying is that we can divide data into various groups. So that's what we are trying to say. When we talk about quantiles, what we are saying is that we can divide data into various groups. So that's kind of, I'm loosely defining quantile for you. So this is a quantile. So you could say something like 0.5 quantile. So you can say 0.5 quantile is 4 feet. In other words, 0.5 refers to 50%. So 50% of the students are less than 4 feet and 50% of the students are more than 4 feet. Now, a term that is closely related to quantile is called quartile. So that's Q-U-A-R, quartile. Now, what quartile refers to is that you divide the data into 4 parts. So quartile refers to that you divide the data into 4 parts. So let's assume, for example, your data is distributed like this, kind of in a normal distribution. Now, in a normal distribution, we know that 50% of the data will be on this side and 50% of the data will be on this side, and somewhere here. So we know that this is 25% of the data. That's 25% of the data. So remember that the area is probability, and that's X for you. So quartile means 4 parts. Now there is a term called interquartile range. Interquartile range. So what interquartile range means is that the range between, so this is quartile 1 for you, that's quartile 2, and that's quartile 3. So interquartile range means the range between quartile 1 and quartile 3. So why do we use interquartile range? Now, if you have a series of data, let's assume that you don't want to look at the extreme cases because the probability of having these extreme cases is quite low. You can see the areas are quite low. You might have them, it might take place, but the probabilities are quite low. So there are some instances you might just want to know what's my interquartile range. I have a series of data. What's my interquartile range? So that means you want to know this value and this value. In other words, tell me the range where there's a high chance that I might get. So let's assume that these are your asset returns. If you know your interquartile range, let's just assume your interquartile range is between minus 10% to plus 15%. So this is minus 10%. This is just hypothetically to 15%. So what that means is, if you get to know that your interquartile range for your asset returns is between minus 10% to 15%, what you're trying to say is that there's a high chance that we might end up somewhere in between. That's what basically you're trying to say. So you can see that interquartile range can be a useful parameter to make some analysis, because remember, these probabilities of beyond getting anything less than 10% or more than 15%, there is, of course, there's a probability, but the probabilities are very low. You can see that. So in those instances, interquartile range helps you to perform some analysis in addition to some of the moments that you have already learned. So a Condyle function is quite useful. So remember, we can use median, and also we can use interquartile ranges to perform some further analysis on our distributions.